I forgot. I was being so good for a while there about recording. You got to run. Okay, well, I'll record from here at least. Sorry about that. So I missed the first 30 minutes of class recording, but we're talking about parameterizations, and we were talking about parameterized the unit circle, and this is this kind of the whole invention of trigonometry, parameterized the unit circle. So now if we go to this handout, the parameterization handout, if we look at page 2, here's some examples. Let me just show it for a minute. So yeah, what if we wanted to change the radius? What if we wanted to just parameterize a circle of radius 5? What would we have to do to this parameterization? How could we change it? Yeah, we just actually scale these by 5, right? 5 cosine t, 5 sine t, right? So for question 4 on the handout, so yeah, again, if you're not looking at the handout, please download the parameterized curves handout. But I'll just leave it. Okay, so example. Circle centered at the origin, radius 5. Well, that would just be x equals 5 cosine t, y equals 5 cosine t, sine 5 sine t. 0 less than or equal to t less than or equal to 2 pi. Okay. So that's all I got to do there. I mean, sometimes I'll just write this instead of the vector form. You're at one or the other. Okay, what if we want to move the center of the circle? Sorry? So right, okay, so let me write this example down. So there's the equation of the circle, but there's also the parameterization of the circle. So let's actually write both down. Let's write the equation, because really the parameterization should satisfy the equation, right? Like I didn't say that, but for the unit circle, we do have cosine squared plus sine squared equals 1, which is equivalent to x squared plus y squared equals 1, right? So, and there the equation of the unit circle radius 5 would be x squared plus y squared equals 25. And you can tell if you plug those in, you would get on the left-hand side, you'd get 25, right? So circle of radius 2 centered at 3, 5. So the equation, which is I think what Milano was getting at, right, is, what is it? Well, x minus 3 squared plus 1 minus 5 squared equals 4, 2 squared. Right, that's the equation, but the parameterization should satisfy the equation. So what do I really want x? Can anybody see kind of where to, like what I want to go for what I want to set x equal to in terms of t to make this work? Yeah. Yeah, like you actually want to add a 3. This is where it's actually the normal thing. Like, right, we always do this minus when we're shifting equations. But parameterizations, you can actually add, because adding really just shift the thing over 3 units to the right, right? So if you try x equals 3 plus, and I guess it's going to be 2 cosine t, y equals 5 plus 2 sine t. Look how perfect that is, because now when you subtract 3, you actually get 2 cosine t. And when you subtract 5, you get 2 sine t. That's exactly what you want. So here you're actually shifting it the direction you want to. You're just like shifting over 3 and up 5. So it makes sense, right? So we just shift over 3 and up 5. That's shifting the x and the y. Okay, so it's kind of nice. Or maybe if this is so, maybe this, I was going to say this equation explains this parameterization, but maybe this parameterization actually better explains this equation. which is that this is very natural. You're just moving the x over 3 and the y up 5. But then to make it satisfy the equation, you have to subtract these constants over to their side. You know. Good. What else did I say? Oh, 3D space. Okay, so we're going to start to do things in 3D. So now what if we had, so yeah, number 6 from the handout is what if we have a circle of radius 3 which lives in a plane parallel to the xz plane, so that says, and centered at the point -1, 4, 5. Ooh. Okay. Just write some of this down. 3D. It's in a plane parallel to the xz plane. Radius 3, is that what I said? Yeah. Radius 3. Center -1, 4, 5. Okay, so let's think this through. If it's in a plane parallel to the xz plane, we're basically just trying to find x, y, and z in terms of t, right? In terms of our parameter. So if we're in a plane parallel to the xz plane, what does that mean? Y is constant, right? The xz plane is y equals 0. And so if we're in a plane parallel to the xz plane, then y is constant. So what's y equal? Yeah, y is going to be just 4 always, because we're in this plane parallel to the xz plane. And now we want, now I think we can just do what we did up here, right, for x and z. So what should x be? Yeah, -1 plus 3 cosine t, and then z will be 5 plus 3 sine t. And I think that'll work as an answer. Right. So that's just because we're in this plane. Right. So that makes some sense. By the way, you can do things like switch cosine and sine, and it'll still trace a circle. It just traces it differently. I mean, that's another thing that might be worth, like if I pull this, let me pull this other board back down. You know, there are multiple answers. There's multiple ways to parameterize the same object. So like I could, like the cosine sine parameterization starts here and traces this way, right? It traces that way. This is like t equals 0. This is t equals pi. Up here is t equals pi over 2. You can label the points with the corresponding t value if you want. You know. So if you tried something like sine t comma cosine t, how would that trace? If I switch the x and y, how would that trace the unit circle? Yeah, where does it start? If I switch cosine and sine, what's the t equals 0? Yeah, it's the point up here, right? We basically swapped x and y coordinates. So if we did sine comma cosine, it would start up here and it would actually trace this way. It would trace clockwise. So if you want to trace the circle clockwise, you could use sine comma cosine if you wanted. Not really, because it's a convention, right? I mean, it'll matter when we're doing integrals over curves. But it doesn't matter if you're just trying to trace the thing out. But it's sort of interesting to think about. I guess, yeah, and in fact, the next section of the handout's about that. If you have the same curve with different parameterizations, like it talks about the fact that like, if you're parameterizing y equals x, you could really make x and y any function of t, as long as it's the same function of t. And it would still trace out at least part of the line. I actually want to go down to maybe just for the last 2 minutes because I've got some nice animations. Might skip. Well, the other thing is also, share screen here so people know what I'm pointing at. I mean, there's also nice things. So like here, right, you could parameterize the line y equals x in a different way. You could also parameterize circles different ways. This actually traces the circle twice as fast. If you do cosine 2t sine 2t, it just traces twice as quickly because like you just need t to go from 0 to pi to trace out the circle once. So you can think about changing those things. Oh, we actually just answered number 10. T equals 0 corresponds to the North Pole. Traces the circle clockwise. We just said if we switch cosine and sine, that happens. And you can do pieces of curves, but let me go to lines. So, and there's a picture here from the book. But I actually have, because lines in space are going to be kind of an important thing. An object that we want to be able to analyze, but we haven't really done so far. I think I said that earlier in class. You could imagine x, y, and z being linear functions of the parameter, and that would actually trace out something linear. But let me actually let me share the entire desktop instead of just that. Yeah, so in fact, if I go to, there's a Mathematica notebook that I think has some nice illustrations of this, of how I could actually trace, if it wants to open. Open for me, please. Where'd it go? Oh, here we are. Okay, yeah, so, sorry, let me make this bigger. Oh, here's interesting. So like, if you want to trace a line in the plane, I'll do plane first and then there's in space down here. So I wrote some code to do this. Like, if you think about how you would trace a line, one way you can think about it, maybe I'll just talk about this with pictures today, and then Monday we can do this more systematically. But you know, this is where the vector idea of parameterization is helpful. One way to describe a line is you start from the origin and you go out to a point on the line, and that's what the blue vector is here. It's like I'm just going to start at the origin and go out to a point on the line. And then from there, I'm going to follow this orange vector, which is I'm going to just follow the direction of the line, right? So if I want to find more points, like I can find one point on the line by just finding a point on the line and going from the origin out to that point. Then I can find other points on the line by like following, there's some sort of direction vector of the line, right? The line sort of has a direction vector of its own. And if you follow that direction vector, but you scale it to different magnitudes, then you can actually land on different points on the line. And that's sort of what this animation is showing, right? Like if I follow the direction vector, but I scale it by different amounts, then I can trace out different points. Does that make sense? Just purely as like a conceptual idea. Like I haven't written any math down yet, but you can imagine this is a way to trace out points on the line. Is you need to basically specify a point on the line and the direction of the line, a vector that follows the line, and then you can find points, all the points you want just by scaling that direction vector by different amounts. Yes, no, maybe, kind of. Here's a 3D version of the same thing. Here's some line in space, and this is where it's interesting, because again, if lines in the plane, we can always write down just as an equation y in terms of x. But in space now, I have this line, and it's the same idea though. I have this blue arrow going from the origin out to a point on the line, and then it's a little harder to see, but there is a orange vector there that's on the line. There was some way to actually zoom in. No, that's not it. Wait. Ooh, that was fancy. Is that anything useful to me at all? Yeah, you really can't see the arrow for some reason, but I mean the body of the arrow. You can see the arrow, but not the rest of the vector. But anyways, it's a little bit hard to draw this stuff. So this is an idea, right? It's sort of like, okay, I'm gonna follow, right? And so we need to figure out how to write that down is the question. So let me go back to the handout for a second. Just to think of, and this is an idea, right? It's like you pick your sort of initial, like this R naught is gonna be this initial point on the line. So that'll correspond to t equals 0. And then I have a v vector, which is the direction of the line. And if I do R0 by itself, I just end up at this point. If I do R0 plus V, I end up at this point. If I do R0 plus 2V, I end up at that point. If I do R0 plus 3V, I end up at that point. If I do R0 plus negative 1V or R0 minus V, I end up at that point. And so you can imagine if I wanted to end up between 1 and 2, I could use a scaling factor between 1 and 2, right? If I wanted to end up at this point right here, then I could use like t equals 1.5. I could scale the vector by the v by 1.5. So maybe just as a thing just to write on the board and just to think about for Monday is I'll just say that there's this really abstract vector way of writing down lines, but I'll get into like examples and just really seeing it concretely on Monday. But yeah, so lines. If R naught represents a point on the line, I guess a vector from the origin to a point on the line, and V is a vector sort of along the line, parallel to the line. Then there's this idea of saying, okay, what we do is we go out to the line, we go from the origin out to the line, and then we follow the line by different amounts. And that's what the parameter is like the amount that we're scaling the V vector. So this is like origin out to the line. And this is like follow the line by different amounts t to get different points. And so that's kind of this abstract way of thinking about it. So we can see this actually is going to give us equations that make sense. And so we'll get more into that, I guess, on Monday. But you might look at this handout over the weekend if you would like to, because it's fun. And there's stuff in section 17.1 of the book. Okay, so we'll pick up there. Just we're out of time now. So we'll pick up there on Monday. Now you know what trig is for. I mean, I think you knew, but this is one way to describe mathematically.
Thank you.
Yeah, oh, thank you. Remote folks, I will stop the recording. Sorry, I missed recording the first 35 minutes of class, but oh well.